Hello, welcome to this walkthrough video for the solutions to the spring 2022 midterm 2. Let's just get into it. I'm going to break the video up into chunks and we're going to start with problem 1. So problem 1 says, consider a binary min heap, which means smallest values at the root, which is stored in an underlying array. Answer the following, assuming that we use the implementations given in lecture. And so the first thing it says is, suppose our heap initially contains 7 elements, which are all numbers and they are all distinct, or all the values are unique. For convenience, we've numbered the array elements starting from 1 rather than 0, and there is no implied ordering to the numbers A through G. So A through G are just sort of the labels we're sort of putting on the nodes or elements, almost like variables like X and Y in math, and they don't actually have anything to do with the value of those elements in the heap, right? A through G are just our labels. And so I think the most helpful thing to do at first is to draw out what this heap actually looks like if we do the like tree representation, right? And so that's going to look like A at position 1, we have B at position 2, C, D, E, F, G, and these, oops, I've messed up the numbers. Okay, these numbers are just which position they're at, and this is what our heap looks like. And so again, emphasizing just one more time, A is not actually the value of like the number there, it's just sort of like our fill-in, our stand-in, so we can refer to it by something. And so the question says, after removing the smallest value from this heap, G is in position 5. What values are in the remaining 1 through 6 positions of the array? And so we'll do the normal min heap removal process and just see how does that end up. And so we know, as always, when we're removing from a min heap, we pop off the root, which is the minimum element, and we replace it with the thing that used to be in the spot in the bottom row all the way to the right. And so here that was G. Now we have to swim down. And so typically, because we don't actually know the values of G, B, or C, we wouldn't normally know, oh, does G swap with B or C, right? Because the values are distinct, but we don't know between B and C which one is smaller. However, we have received the hint that G has to end up at spot number 5, right? And so in order for G to somehow swim down to 5, it needs to swim along this path that I've just sort of drawn out here in green. And so we know G is going to swap with B. B's here now. And then G has to swap with E again. So keep swimming down in order for us to end up with, in the scenario where G is at position 5. And so this is the remaining, this is sort of the end result after popping off the min. And so we can fill in this array and we know going just in order 1, 2, 3, 4, 5, 6, it goes B, E, C, D, G, F. And that's 1A. The next thing says, after part A, when the heap has 6 elements and G is in position 5, which of the following statements must be true? Check all that apply. And so this one's just asking about basically the like comparative size of each element. Now remember, the heap property only says a parent must be greater than all of its direct descendants, or sorry, smaller than all of its direct descendants. So B has to be smaller than everything. E just has to be smaller than D and G. C has to be smaller than F. But notice how there's no statement in the min heap property that says anything about E and C comparatively, right? Unlike a binary search tree, we have no guarantees about like sort of the differences between the left and right. It's just the parent and its descendants, that type of relationship. And so the only guarantees we can make are ones between like parents and descendants, or like things on the same sort of path from the root. And so we know that B has to be less than C because B is a parent of C. We're in a min heap, which means this one cannot be true, right? Smallest things need to be on top, so B is smaller than C. With C and D, we see they're not on the same path to the root, or they're not ancestors of each other, so nothing here. Same for this one. We do see that D and E have this sort of like ancestry relationship, And we know because it's a min heap, smaller thing is on top. So E is less than D. And so we're going to bubble in this one. We keep going. We see G and D again are not, one of them is not the parent of the other or ancestor of the other. So nothing for these. With G and E, again, we see E is a parent of G, so E must be smaller. So we're going to say G is greater than E. And then for G and F, again, there is no like grandparent-child, grandchild relationship here. And so this is part B. Then part C says, suppose the heap again contains values A through G as it initially did in part A. So we're sort of restoring the state. And we enlarge the array so that it can hold 10 elements. Then we add 3 values, H, I, and J, and we want to know what values could possibly be at position 5. And so I'm going to sort of restore this heap just so we can see D, E, F, G. And we're going to first insert H. And so the way I'm going to keep track of this is I'm going to draw in green what things could possibly end up places. And so if I insert H, initially it's going to end up at this location, right? Because it has to go in the bottom row, filling in as much to the left as possible. So it's going to start at position 8. But theoretically, H could swim all the way up along this path. And so H could also be here, or here, or here, right? So far, so good. Then notice that if we do those swaps, if H swaps with D, then D could be here and H would be here. If it kept swapping up, then B would be here and then H would be there. And A could possibly be here, right? Because the idea is that when the elements swap, they swap upward. And just to make that more clear, I'll actually show what this would look like again, just to make it more clear. If H starts here initially, it's possible that H is smaller than D. It's possible that H is smaller than B. And it's possible that H is smaller than A. And so H could potentially end up swimming all the way up to the top. And so we can see how everything I've shown in green here is possible to end up at these positions because of the whole swapping. Then what happens if I insert J? Well, J initially is going to be here, but it's possible that J is inserted here and whatever is here could be swapped down with J, right? And so if that was the case, whatever was here could end up here, which means B, H, and D can all end up at position 9. And J could end up here. Okay. And what if J were to move up again? Well, then it would be possible that J swaps up here, and looking at sort of the elements here that aren't already on this list, you see A would then move down if A and J swap right here, right? And so A gets added to this list. B and H were already there, so there's no need to add these. And if J kept swimming up, it's also possible J ends up here. And so this is sort of a list of possible swaps. Now, finally, we're going to see what happens when we add, I realized I added J before I. All of this was supposed to be I. Good thing they look so similar, right? Cool. Now we'll actually add J. And so J is going to belong as the left child of E at position 10. But it's possible that J swaps up with E and ends up at position 5, right? So J could be here and E could be here. And what if J kept swimming up? Well, then J could end up here and I, A, H, and B, whatever was here, if J moved up, could possibly move down if J swaps. And then finally, J could swap all the way up. But at this point, we figured out what we need, which is that the things that could possibly be at 5 are J, E, I, A, H, and B. Quite a few options. So that's J, E, I, A, H, and B. And that is all of problem 1.